potentially an easier question is what things changed. Got a lot of moving parts on that.
Where? Oh, never mind.
Okay, so since I think you saw the tricky part, let's put some words to that. Okay, can you walk me through what your question was and why you backed away from it?
Well, I was just gonna say, where the heck did that hydrogen come from? And then
Hydrogen, this hydrogen then?
Yeah, but then I was not paying attention to the things up here.
Okay. So not the question I thought you were going to ask.
You think I was gonna ask what R is?
Related to that. So it's less what R is. So R is a holdover. It's a placeholder. R typically means hydrogen or carbon. Okay? But really it can be used to mean anything. The primary meaning behind it is it's just a placeholder. It's not what's doing the chemistry, so we don't care about it. We're going to ignore it and just let it kind of run off into the ether. So what changed?
The R with
Two lines.
yeah.
So notations, this is R, R prime, R double prime.
The R double prime go down next to the
Okay, I want to push on that a little bit. Down. Where is down in this? Where is down in any organic chemistry reaction?
replace.
Where is the direction down in organic chemistry? It's non-existent. So telling me it's aimed down doesn't hold any meaning whatsoever. Okay, so what you're trying to tell me is that this R prime, instead of drawing it up, is drawn down. Well, if I draw it down, does that change the identity? Oops, yeah. Is this now a new structure from that? So, and you're not wrong to notice that, but where we have to be really careful is notice the things that actually have an effect on the identity of the substance. Until you can call those out, you're looking at the wrong place. Okay? You're watching the magician look at, and you're watching the misdirection, not what's actually happening. But I can redraw it like that, so we have that double prime.
So we add a big group with R, 3R and 1 OH.
So you're saying this was somehow added. That's fine. I'm just trying to reiterate your words kind of for the recording. Where did that come from? Okay. If we look to the arrow, it says sodium hydroxide and acid. Does it say anything with R's? No. So again, where did that purple circle come from? This is a very hard reaction. What do you see as common in that purple circle? Not even what you see as common. Do you see anything familiar within the purple circle stuff?
The hydroxide, OH group.
Where do you see OH? Outside of the purple circle.
You say outside?
Mm-hmm. Because I'm saying, look at the purple circle and say, what's familiar within it? Okay? So if there's something familiar within it, you're saying that something else appears somewhere else in the thing. And it goes, oh, there's that thing. We're trying to find the pieces where those things came from, where they went to. So you're saying hydroxide. Where do you see hydroxide? Outside the purple circle. I see hydroxide right there. Okay, so Lindsay agrees with me. Okay, not a bad observation, except that we have this nasty or word. What does that mean?
Hydrogen.
This reaction can work in the presence of sodium hydroxide or in the presence of acid. Why does that become a big deal? It's or, which means I could delete this. And if I delete that, where's OH? It's not there anymore. Okay? So we need to find where that OH is. Okay? And this is challenging. Okay? So what you're trying to do is find those pieces and find their representations in the starting material so that you can figure out how they reacted. Okay? This equation is as balanced as we get as far as organic chemistry goes. Okay? So again, looking within the purple circle, do we see anything familiar within it? Okay, so, and we like looking at that OH, okay, so, and you at least added a word that I want to work with a little bit better. You started saying hydrogen. Where does hydrogen show up? Generally.
Not involving this.
Not necessarily involving this. Attached to carbons, and where do carbons show up? Think of all the stuff we've studied this semester. How often do carbons show up? A lot. Everywhere. It's literally the study of the class. So what you're zeroing in on is the hydrogen, which shows up everywhere. Is that going to be really easy to narrow the field about what changed if you're looking at the hydrogen? No. Okay. So we could go alcohol group. Do you see an alcohol in the starting material? No. Okay. Try again. Okay. And for the record, if you're afraid of being wrong, we've already gone through 3 wrong answers. Wrong isn't the problem. The problem is not venturing that guess to see what's out there. So within the purple circle, I know it doesn't look like a circle, but close enough. What do we see within the purple circle that we see outside the purple circle? There's an R here. There's an R here. There's an R prime here. There's an R prime here. There's an R double prime here. There's an R double prime there. Okay? And looking to those hangers on is not a bad idea. It's not a bad place to go. But where I would probably push more towards is our carbon backbone, our carbon structure. There are 2 carbons that connect all those R groups. How many carbons connect the R groups in our starting materials? 2. That's a 1-for-1 match. Okay? But if I look at the product has 2 R groups, 2 R prime groups, 2 R double prime, and 4 carbons. What does that mean had to happen in the starting material? How many of these had to be there? What does that 2 mean? So we started with this, and we became this. What changed? And we just have to talk through it. So received a hydrogen. What hydrogen are you talking about? Red hydrogen. Okay. So we're talking about gaining a hydrogen. Okay. What else changed?
Could you say size or no? 'Cause it. The double bond breaking into single bond.
Yeah, I would say that's a really big one. Okay. We have the loss of a pi bond. And as soon as we see loss of a pi bond, what should we be screaming as what happened here?
Elimination.
Right idea, wrong word.
Addition. Addition.
This is an addition reaction. We've lost that pi bond.
So we're only looking at the purple part, with, like the purple circle. when we
So,
say
What we
addition.
were looking at, where we started, and so deciding why we were looking at the purple circle, that's going to be a question for Annie. Right? But what I would kind of talk through is what Annie went back and forth and did was notice that this purple part was new. That this black part, the outside purple circle, was already there. So the new thing was what this purple circle was. That's great. We then had to decide where that purple circle came from. So we could go back and look at our materials and say what things were there. Okay? If there was a highlight, oh, I see an OH, so you jumped all over the OH. I would say, oh, well, there was sodium hydroxide, but I noted the or, which meant that that OH did not have to be present. Even if it was present, where the heck did the other carbons in R groups come from? Right? They had to have come from somewhere. This is where we could recognize that, oh, that meant we needed a second molecule. It told us we had a second molecule. Right? Does it have to tell you that? No, it doesn't. Because when we were on chemical reactions, we never run single molecule reactions. That never happens. They run at much larger scales. You're looking at tens of thousands of these molecules, tens of billions of these molecules. Right? So I don't have to specify the amount. But this format was designed so that I had that information. When we write that second information down, now we could have a conversation about, now I see all of the pieces. The question becomes, what were those big changes? We could say, yes, I gained a hydrogen because I didn't have that hydrogen on there. Okay? We're going to come back to that in a second. Okay? We could say that when we look, we have 2 pi bonds here, we have 1 pi bond here. What does that mean? It had to be an addition. I lost a pi bond. Right? What we're trying to do is recognize those changes and then put labels on them so that we can have a conversation about those changes. The same thing is going to happen in any biochem class. What you're going to do is look at a chemical reaction and say, well, what things changed? The one thing that changes when you move into a biochem class is it's not going to be just random things. It'll be like, oh, this is glycolysis. In glycolysis, we do this. And then what do you have to do? You don't have to recognize those patterns. You just have to memorize it. So what we're trying to set you up with here is to be able to find those patterns, to look for those changes so that you can identify them and you can start to use words to describe what's going on within them. Kind of, sort of?
I'm a little bit confused. So when you're saying you lose a pi bond, we're just comparing, we're splitting that molecule into 2 and we're comparing.
Yeah, that's kind of weird.
Okay. We said this was our product,
Yes,
this is our reactant.
but they're together in the product. Like
All
we're splitting them
products
up.
are together.
I know,
So
but,
what you are looking for is the pieces of your reactant that are in the product.
okay,
That's all you're doing.
okay.
Right? So what Annie went through and did, presumably, I'm putting words in your mouth, hopefully the words are okay, is that she saw R prime, R double prime connected to these carbons in the carbonyl. And she
Right.
went, that is our starting material.
Yes.
And then she said, OH is not in my starting material.
Yes.
Therefore, all of that piece was new.
Yes.
Where did it come from? That was my question.
Yes.
If that is new, where did it come from? Did it come from the OH here?
Well,
Maybe, but that doesn't explain the existence of those other carbons.
yeah.
So what does that mean? Where did they come from? If they didn't come from here, they had to have come from another molecule. Why does it have to be another molecule? Why can't it be the exact same one?
I don't know.
How many carbons are in one molecule?
Here, there's 3.
2.
2. We don't know what the R groups are, so
Oh.
point.
Okay.
2. How many carbons are in our product?
4.
4. Can I use the exact same molecule to make 4 carbons? That's physically impossible at all levels. We can't do that. We could take carbon and if we were really good, somehow nuclear split that into smaller atoms. But we aren't trying to split it into smaller atoms. We're trying to make equivalent atoms. I don't have enough matter from this thing to make this. Period.
Okay.
So the question is again, where did that come from?
I guess I don't understand the losing the pi bond.
Okay. How many pi bonds? So this is what we started with. How many pi bonds are in our starting material?
So we're assuming that we started with 2?
Are we assuming that? Okay. So when you make the statement, I'm going to assume this, you're making the statement that you have no evidence to support that you need 2.
Because there's a 2 there, that's not just a number, this is like problem number 2.
That's not a random 2. But then I also said, does it have to say 2? No. So what evidence do you have that makes you go, I have to have 2?
Because how else would you get there? But that's...
How do I get 4 carbons if I only have 2? I can't. It doesn't happen, which means I need 2 of this molecule to get to 4. How do I know I need 2 of this molecule?
Because there's 2.
2 plus 2 is 4. What if I ran the reaction and somehow or another, different system, 1, 2, 3, 4. Okay? Don't worry about the details around up here. 2, 3, 4, 5, 6. How many of these did I need to make that?
3.
Why?
6 carbon.
And the starting material is 2 carbons. That's why I know I need at least 3. That's how I can get that. That's conservation of matter. When I look here, what's happening? I have 2 and I end with 4, which means how many of these must I start with?
2.
At least 2. So now I can change my drawing. Because when we look at it initially, all we're looking at is one molecule, and it's really hard to see that. So what did we do? I redrew it so that I could see both of them. We know both of these are now our starting material. So this black box is representing our starting material with all the pieces that we would potentially need within it. Okay? Of our building blocks, our carbon units. Okay? What changed to go from the black box to our product? To our red box. Well, how many pi bonds are in the black box?
2.
How many pi bonds are in the red box?
1.
Which means
I see, we lost a pi bond. I see that now. I didn't know that we were working with 2. Sorry, I missed that.
okay. We're processing through all of those changes. And sometimes it's not easy to see those, which is why we have to redraw it. Okay? What we're trying to do is make this visible to us so that we can see those pieces. Okay? This is why in Unit 1 you drew things a whole bunch. The idea was to get used to those drawings so you knew where those things were, so that you didn't have to draw as much. We now add on a layer behind reactions, and now we have to reconsider those things. And it may be really hard because you're trying to process reactions and structure. So simplify. Draw more structures to represent. If we've got a loss of a pi bond, we know this is an addition reaction. Right? To do an addition reaction, what has to happen? Lose a pi bond. Ah, what's that? Gain 2 sigma. Okay, we have a gain H. Is that a sigma H? How is the H connected to our structure? Connected to the oxygen. What connection is making that? Is that a sigma bond or is that a pi bond? It's a sigma bond, so I gained a sigma. Awesome. But if I'm doing an addition, it's gain of 2 sigma. What's the other sigma I gained? Is there too much in the red box? Should I erase some colors?
No.
Don't erase colors. Okay. I want to erase colors. The oxygen lone pair is not a bond. That's a non-bonding pair of
The
electrons.
second carbon, or the fourth carbon, I should say.
Wow, I just took a picture.
Encircled in the purple. That's connecting the green R and the purple R.
Green R, purple.
Right? Yes, that one.
Okay, is that a bond?
Well.
Actually, I think I can do this one. And I'm not saying you're wrong necessarily. I'm just asking, is that a bond? There we go. We got my little arrow. Is pointing to that a bond? What makes up a bond? 2 electrons. 2 electrons where?
Another hydrogen.
What's that?
Another hydrogen.
We need to answer the bond question first before we go back to that. How do I know I have a bond? Yes, 2 electrons. 2 electrons where?
Connecting to atoms.
Call it a blue circle up there. Where's my bond?
The lines in between
Oh, finish your statement. Do it all the way.
Between the O and the H.
Okay. The bond is the line that connects 2 atoms. Yes. Okay, that is absolutely the bond. So when we go through to look at our product, what we need to go through and do is say, where is the new bond? Because if we said we had an addition, we had to have gained 2 sigma bonds. You're doing great,
Okay.
but Kimball did raise her hand.
So when you lose the pi bond that's attached to the OH, there's an implied hydrogen there.
Implied hydrogen where? On this carbon?
Yes.
Okay.
2, 4, 6.
Okay, it's really, really small. I'm going to try and do this on the screen. How many electrons right here?
2, 4, 6,
6, 8, which means, you just did the What was the
8. It's not there.
There's no hydrogen there, yeah. Okay, and Annie was pushing this too. She said hydrogen. Maybe Annie confused you. Oh, dangerous Annie. Okay, there's a hydrogen.
I have no idea.
Would it be the bond that is in between the 2 carbons that I originally thought, right?
You only gave me ever 1 carbon, so I can't answer
so
that.
The wrong carbon, the original carbon,
Where's my arrow? Sorry.
and then.
Because we were pointing here.
Yes, and then the carbon to the left of it.
Here. So
Yes,
that bond.
Yeah, that bond.
So that bond is new.
Yes.
Okay. That's the bond between a carbon with a blue R group and a carbon with a purple R group, right? There's a carbon with a blue R group and a purple R group. Is that bond there?
Yes.
So was that the bond that was made? If I can point to the bond in the starting material, did it get made?
No.
No. Okay. So maybe it was this bond.
So it's the green and the blue? Okay.
How about this bond?
Mhm.
There's the new bond. And here's where I'll drop in another color on it. That's the new bond.
It's connecting your two molecules.
It's taking this carbon and it's connecting it to this carbon. I didn't want a solid line, I just realized. Somehow or another, this reaction is facilitating a connection between those two. Okay, so that is the gain of my sigma. Okay, and officially, if we're going to talk about it, it's not just a gain of an H, it's the gain of the OH. It's a gain of the sigma between carbon and carbon. That's now an addition. Kind of, sort of? So what we're looking at is those changes to try and pinpoint how this chemical reaction or what this chemical reaction did. That's it. How it does it is now the mechanistic detail behind it. Okay? Because we should be able to look at this and be like, that doesn't make physical sense. It should never be able to do that. Why not? We'll call it our green circle and we'll call it a blue circle. What can you tell me about the green circle? Or green dot? Can you tell me about that carbon right now?
Something, because
Yeah, you could go with for something.
It has one hydrogen.
To satisfy what?
It's octet.
The octet. So it has 4 bonds. There's an implied third hydrogen, which means, could it possibly make a new bond to the blue atom?
Not without losing that hydrogen.
It would have to lose something, and we're going to come back to what that loss is in a second. Take a look at the blue atom. What does the blue atom have? Can't have 5 bonds. It has 4 bonds. It has its octet. There's 1, 2, and 3, 4. There's no implied hydrogen because that would exceed its octet. It has that double bond. So again, it can't make the bond as well because it has its complete octet. Okay? So something has to change. We already know some things that had to change. Okay? If we go through and just assume that this is the blue carbon and this is the green carbon, okay, what changed to the blue carbon?
The bond to oxygen became sigma.
I can't complain about that. You give me enough detail. What I wanted to hear was the pi bond broke. Yeah, the pi bond broke and we're left with the sigma. Why did that need to happen? What did I need to make? I need to make that new carbon-carbon bond. So the pi bond was what was breaking in that process. If we go back to the green atom, what happened to the green atom allowing it to make that new bond?
It's hydrogen.
It lost the hydrogen, because if we look at the green atom in the product, does it have that hydrogen anymore? No, it does not. So by piecing together all of these subtle changes, you can start to predict what overall happened. So in this particular case, we had to break a hydrogen bond off of here. We had to somehow make that bond. We had to break this bond, and then we had to make another bond out to the hydrogen. So there's kind of 4 things that have to somehow scaffold together to allow this reaction to complete the overall cycle. Okay? That can't all happen at once. Okay? So we would then have to break that into individual mechanistic steps to decide how that's going to occur. that whole process on how that's going to occur is now going beyond this unit. Because what we're, I forget why I was walking away. Okay? That's now moving into, ultimately, for this reaction, unit 4. Okay? But what I want you to be able to do is to find those changes now so that our conversation in unit 4 isn't what the hell changed, it's how did that change? It shifts the focus and gets to a deeper understanding of what's overall happening. So the point here is to find those changes, acknowledge what those changes are, and start to use some words to describe what's going on behind them. Okay? I'm not saying that's easy. That's why we're talking about it now, trying to get you to that point so that we don't have to talk about that and how it's happening later on. Kind of, sort of?
I have a super quick question. For, not like this specifically, but just losing your pi bond, it's always going to connect somewhere else, right? It doesn't just cease to exist.
Okay, and that becomes the fun question. Right? What happened to those electrons? We can't destroy them. They have to have been moved somewhere. The question is, where did they get moved and when did they get moved? Okay, that's pushing at some deeper level questions that I would argue move into, again, unit 4, because in this case, we're talking about breaking of the pi bond. If we shift your question to, instead of breaking of the pi bond, how about making a pi bond? Where do you get electrons from to make a pi bond? Well, that's now going into the next unit, and we're looking at elimination reactions, where elimination results in the formation of a pi bond. And so we're asking that question, how do I get the electrons to make that bond? Where are they coming from? And when we talk about anything in nutrition, anything in biochemistry, that's exactly what's happening. You're just shuttling electrons around, and that changes the overall structure into those new pieces. Sometimes they're easy reactions, sometimes they're really complicated. Right? And depending on what has been studied, you may or may not go into the levels of detail behind those. But the point here is to set you up so that you can recognize those changes and you can start to have that conversation. Kind of get it? Did I answer your question?
Kind of. It's always whether it turns into another sigma bond, or it can just be like a lone pair somewhere too.
So, and
It's
that's,
not gonna just like.
yes. So if we get much more specific to your answer, and I think I was trying to avoid being too specific because I didn't want to get into unit 4 stuff. Where did the pi bond go? That pi bond went to make the bond with the hydrogen. Because what charge would we expect the hydrogen to be? Positive. And if it's positive, can it make any bonds? No, it needs electrons. So what does the oxygen have to supply? Electrons. Where is it getting them from? That pi bond. So when we're talking about our addition reactions, the pi bond is almost always being used to make a new sigma bond.
And it's not making the red line one?
And it is not making the red line one. Okay? How would you know that? That's knowing the mechanistic detail behind this reaction. I don't expect you to know that. I expect you to process it. Okay? And what do I mean by process it? Can I delete everything? Okay. This particular site formats things in ways that I don't particularly like, and it's also super small. Well, maybe I can make it a little bigger. So for instance, when they show lone pairs, what do they show the lone pairs as?
Dots.
They don't show them as dots. They show them as lines. Yeah, I think that's really, really confusing, personally. Okay, some people are okay with it, some people aren't.
Yeah, because it looks like that could be a negative.
Yes.
That
Right.
could be a
And
negative.
even when you get up to this oxygen, there is a negative next to it. Also, one of the reasons why I like circling charges, to try and emphasize them out away from the structure. So if we look at our overall mechanism, okay, this is for the base catalyzed version of it. We won't stress about the acid catalyzed because it's going to do the same thing, it's just more complicated. Okay, what changed? Okay, so what you'd be getting asked would be, what's the mechanistic step? What happened? Okay, I gotta be a little bit more careful about this when I'm trying to erase those arrows. What happened?
It's saying that the oxygen, is it saying that is that negative or is that a lone pair?
That's negative and a lone pair, technically.
Okay,
It's both.
so it's saying that the lone pair is going to the hydrogen?
Okay. What does that mean happened? I just realized they screwed up.
I was gonna say isn't it the other way around?
Okay. Isn't it the other way around? What do our curved arrows show the motion of?
Moving of electrons?
Moving of electrons. If we turn that arrow around, you'd be moving the hydrogen towards the oxygen. Right? And if you're saying that's the case, you're saying the hydrogen has electrons. We'll ignore that for the moment. And you're taking the electrons and sharing them with an oxygen. What does the oxygen have?
But don't you have to do, like, where's the arrow from the,
We'll deal with that arrow in a second too. If the hydrogen takes the electrons, you're moving them towards the oxygen. What does the oxygen have?
electron?
Electrons. What happens when electrons get near electrons?
That's what
They bounce away from each other and no bond forms. So our arrows show the motion of electrons. So instead of, and this is a problem that generally speaking everybody has, but I've seen a little bit more of your work, Sydney. Okay? And it's for sure a problem you've got. You want to move atoms. I don't blame you.
I know, but I know it's the electrons, but in my head, it's like, I have to show, it's like backwards.
It is. Because, yes, it's absolutely backwards. Because when we consider what we're doing when we do a reaction, we think about moving atoms, and what we're trying to move is not the atoms, so everything appears to be backwards. Okay? So one thing that you can potentially do to help with this thought process on deciding where your arrows are and how they should move would be look at your reactants. How many reactants do we have?
2.
Everybody agree? Okay. Gets a little bit tricky because we have one of our reactants above that arrow. Okay, so we have 2. Before we start saying, well, what do I want to do? I want to make it look like the product. Okay, because now what I'm trying to do is set you up so that you could predict what the product is without actually using any of the curved arrows. That's, again, next level. Okay, but what we want is the skills that can allow you to move on to the next level. Okay, which is more reactive, A or B?
B, because it has the electrons to donate.
Okay, B is more reactive because it is charged, where I would push. Okay, which you described. Okay, because it is charged, it is the more reactive thing, which means my entire focal point with curved arrows needs to center on how do I fix that charge. So what is the charge on the oxygen?
Negative.
Negative. Okay, and now Sydney, you can't answer anymore. Okay, as a negative, what do I need to do to fix it?
Give electron away.
Okay, and so what are you going to say?
Gain an electron? No, it's like the opposite.
So you're falling into the same hole too. So well, for the video's sake, I'll talk through that. We need to gain an electron. Wait, and you said, oh, wait, no, I don't like that. But here's the cool part behind it. You were like, I need to gain, and then you were thinking, and then you said electron. And the instant you said electron, what happened?
Change my mind.
Yeah, you rejected it instantly. Okay? Because as soon as you vocalize, as soon as you write it down, you recognize the mistake. Okay? And that becomes one of the challenges within OCHEM, is that you are so paralyzed to write something down wrong that you refuse to write it down, which ultimately means you get it wrong. But if you can actually try and break that pattern and write it down and talk it out, you can get yourself to make the mistake that allows you to say you are wrong so that you can fix it. Okay? And if we push to what Annie said, which I already forgot. Can you remind me what you said?
Give away one electron.
Okay. Annie flipped it and said, I need to give away electrons. Okay. And I like that word choice. Okay. Give away. It has too many electrons. The problem is it has too many. So I need to give those electrons somewhere else. Because I'm giving them, I need to show where to give them, which means I'm going to be starting my arrow from that negative. And I want to share those electrons with something. What should that something be?
Hydrogen.
Yeah, that's why I erased that. What should that something be?
Something have positive charge.
That something needs to be positive. Okay? Hydrogen's a phenomenal guess, because hydrogen, the vast majority of the times, is positive. Okay? That's doing more work than you're supposed to do, so I apologize. We'll go back. Okay? So in this case, they're saying we're going to give those electrons to the hydrogen. How many electrons would now be around the hydrogen?
2, 4. Well, it's sharing with that carbon.
Did we say anything happened to the electrons in the bond between the carbon and the hydrogen?
No,
No. Which means
they're still there.
they are still there. Which means that hydrogen now has
Exceeded its octet.
4 electrons around it. It has exceeded its octet. That is a problem. Yes,
Goes to the lone pair on the other structure.
those electrons need to be shown to go to the carbon. So this particularly fancy, famous site screwed up their mechanism. They should be adding that curved arrow. Okay? This site has been around for a long, long time and has probably been edited multiple times. They didn't fix this. Why not? Experts in the field don't care. They know what there was trying to be said, and so they don't worry about it. Unfortunately, we're not experts in the field here, so we need to add that extra layer behind it to prove that we know what's going on. Okay? What happens if we do all this? Okay? Well, they didn't show the OH, which is mildly irritating, and I'll talk about that in a second. Okay? We shared electrons with that hydrogen, so there's our hydrogen. That hydrogen lost its electrons to the carbon, so the carbon became negative, and now we've predicted the product. That's all that's happened. Okay, so this is looking at the mechanistic detail behind it. So what things changed?
The molecule as a whole has a charge now, a negative charge.
Cool, our carbon structure has a charge. Okay, that is something that changed. So how can I make my question better? I can't.
You gained a hydrogen on
You lost a hydrogen.
So both those answers are the answers that I want. But I don't know how to phrase the question to not get your answer, unfortunately.
Not charged.
Yeah. Okay. So we gained a hydrogen, the OH gained a hydrogen, and the carbon structure lost a hydrogen. So what chemical reaction talks about the gain and loss of a hydrogen?
Acid base.
All this is an acid-base reaction. That's it. Okay? What's problematic if we decide it's an acid-base reaction?
Then you gotta say the favored.
Now that we know it's an acid-base reaction, you should be able to tell me which way the reaction favors. Does it favor reactants or does it favor products? And yes, as it's drawn, you absolutely 100% can cheat. But we're then going to push the Y's. And if you don't see how you can cheat, don't worry about it.
Your,
It has to do with the charge.
Okay?
And it
When we're
favors-
talking about favoring, what we want to do is look at the charge on each side of the equation. Okay? Look for the most reactive thing. The most reactive thing for probably all of our reactions this semester will be charged. So what we want to do is look at structure B charged and unlabeled organic structure charged. Between those two, which one is more stable?
The line,
Why is the green one more stable?
no,
because, resonance,
Okay, so resonance is a fun thing to throw in there. You're noting that there is resonance. Does everybody see that there's resonance?
the double bond in oxygen.
Okay, so some people are picking up and recognizing that resonance pattern. That's good. If you see a lone pair, you should immediately say, can I do resonance? Can I move those electrons into making a pi bond? I would exceed the octet on that carbon, so I could move those electrons up there. Okay, what that's going to result in would be that resonance structure. Again, try and ignore those curved arrows. We okay with that so far? Okay. So when you're comparing, I guess we'll call it red versus green, everybody good with that? Okay. You're saying green is more stable because of resonance. Okay. Let's walk through all of the things that you should be using to evaluate stability. Where does it start?
charge,
Charge. Okay, so we're comparing red as what charge?
negative,
Negative to green as,
negative,
which means
the same,
no difference. Okay, fair play. What's next?
size,
Size. What are we comparing?
oxygen and oxygen. Oxygen and non-oxygen. Oxygen and carbon.
That's where we first picked up our charge. There's a little bit of gray area here, and we'll come back to that one in a second. Oxygen versus carbon. Okay, which one is more stable?
Oxygen,
Oxygen, which means where does my reaction favor?
the black one.
Your reactants.
It favors the reactants. Goes to the left. Yes. Right? Yes. Okay. Everybody said the products. Okay. I'm kind of on the fence on this one because this is actually a very borderline one and you'd have to really drill into it to figure it out. Okay. And we can do that here in a second. Okay. But you all said resonance was the explanation. Well, it's charge, size, then what's next? Electronegativity. Then what's next?
Resonance.
Resonance. So you all jump to resonance. I like that you're using resonance. That's great. There were 3 other things you should have evaluated first. And if we evaluated size, we're going to see it. We're not going to see a difference. If we evaluate electronegativity, we'll see a difference. That electronegativity trumps our resonance. We should be having that conversation at the electronegativity level, not at the resonance level.
I get confused, I guess, because I'm not looking at, just the thing, just the charge, and then just that atom, that's charge. I was looking at like the whole.
So recently, and by recently I mean this semester, I've added kind of a second tier to this. So we've got charge, size, electronegativity. If you note, I put an A next to it. That A is in reference to atom effects. You will always look at atom effects before you look at molecule effects. That's the 2 people running it down the road at you. You look at who's bigger. Okay? You don't look necessarily at what they're holding right away. Okay? It's a secondary thought.
I
What
thought
you
it
would-
was just like that for resonance.
And then it moves, to resonance, then induction, and then the O. The resonance and the induction are a molecule effect, and then the O is an unfortunate one because it's all over the place.
Is it resonance only that we look, like we do the resonance obviously because it's the whole molecule, but then we only look at the one, where is the charge changing? Because in this case, we make the negative.
And now what you're pushing on is what I would argue a very good statement. If we've got two resonant structures, which of those resonant structures should we be making this argument about? Should we be looking at the left resonant structure or the right resonant structure when we're comparing to our starting material?
Because aren't we looking at the carbon for resonance?
Right now, we're looking at the carbon. Okay, and for resonance is a molecule effect. I don't want to move to the molecule effect until I've exhausted all of my atom effects. And when I look at the atom effect, for sure it's oxygen with the red one, but what is it for the green one? Should it be the carbon? Or should it be the other resonance structure where it's the oxygen that's negative? Which one should I be using for my comparison?
The oxygen.
Why should I be using the oxygen one?
Because now your carbon is.
Which one?
So now what happens is this narrows our field. We were like, oh, I'm going to compare reaction to product, but now I'm just looking at the product and I'm doing the exact same thing. Charge, size, electronegativity. And I'm comparing carbon to oxygen. Where do I want my charge to be? On the oxygen. Oh, please don't screw anything up. I don't know what that just did. Doesn't look like it did anything. This is where, if we go all the way back to stuff we talked about earlier in the semester, particularly as it pertained to resonance, and I made reference to best versus, I'm not actually sure I used this word, useful. You guys vaguely remember that for resonance? Okay. And that we deal with resonance, we're going to have multiple different structures. The best structure is what we should be using to decide between a reaction, the viability of a reaction. The useful structure is the one that tells us what the next step is going to be. So when I go through to make this comparison, reaction to product, I should not be using the carbon as my comparison. I should be using the oxygen. Which then means when I compare oxygen to oxygen, is there a size difference? Is there an electronegativity difference? Is there a resonance difference? Yes, this one has resonance, this one does not. And based off of that analysis, what would we say? Favors the product. Okay? This reaction arrow tells us that, or claims that the reactant is favored. Okay? So there are some secondary considerations that can go into this that can make it more complicated. What I want you to do is reason through these things, and that's why when you get questions like this, what you'll get is me saying, explain. Because what I want to understand is, do you understand what you're reasoning through as you move through this? If you're just using the useful structure to make a comparison and you're saying that one is more stable, okay, that gives me some information. What that tells me is you aren't using the resonance concept, but you're using the rules correct, you're using charges correct, you're using all of that correct. You should get a lot of points. But if you just tell me the carbon one is the product and that one's favored, I don't know why you're picking that. So what I want to see is, again, that explanation that allows me to get there, to be like, why are you picking that path? Okay? Do you actually understand what's happening? Okay? And if you don't, what should you do? Silence is the wrong answer. What's that?
Ask questions.
You could ask questions, or if it's the test,
Skip it.
yes. Skip and come back, yes. But put something down. Okay? Attempt anything. Even in the multiple choice, or not multiple choice, the show your work. Okay? Believe it or not, a lot of those are kind of multiple choice. You're just not given the multiple choice answers to choose from most of the time. You just have to reason through and try and pick something. Well, I'm going to think it's going to do this. So do it. Come up with the best explanation you can. Give me something to give me give you the opportunity to get points. Okay? What else could we look at to decide which way this reaction goes?
PKA.
We could look at pKa's. Okay? If you'd happen to memorize all the pKa's. Did
PKA
you-
is only useful for acid base, right?
Yes. Yeah.
The question of products
Yeah.
versus-
It's really only useful for acid base. Okay.
So you wouldn't recommend spending time memorizing it if we can do this.
Because this is going to work
Lifestyle.
always.
Yeah.
Okay, or work the vast majority of the time, and pKa will only work in that one narrow field. So they both have gaps. Okay, so knowing pKa's will get you some answers, but knowing this charge size electronegativity stuff will get you more than some
That's
answers.
the wider net.
So it's that balance. So our water, I believe, has a pKa of 15.7. Does anybody know the pKa for that starting material?
Or is it something like,
Pretty darn close to 15. I actually want to say this one sits about 13. But that's one I would actually have to Google. I honestly don't know it. Okay. So what does that suggest? Even looking at pKa's, it should favor the products. Why do they have the arrow shown the wrong way? It's a good question. Again, probably one of those typos that nobody really cared about as an expert within the field. Kind of, sorta? Should we keep looking at this one, or do you want a different example?
Different.
And by different example, I mean, can I delete? Because this one right here does give you yet another different example. I dislike how they're showing the arrows for this one. But we have another reaction happening here. Do we want to move in the same vein, or do you want to try and move to something else?
this is all one problem?
This is all one mechanism within the named reaction, the aldol reaction. Okay? So it has multiple mechanistic steps that lead to an eventual product. Okay? And it's not just acid-base, it's got other components within it. Each of those components stacks and builds, and that's how you get the larger overall reaction.
And we're not really dealing with that right now.
So what you're not dealing with, which is a good question, is you're not, if we now kind of look to this one, okay, first off, let's try this. Is this an acid-base reaction? I appreciate your speed, Lindsay, that's good.
No, because
No.
you're not losing.
You're not gaining or losing hydrogens. This is not an acid-base reaction. So this is now going to change the dynamic. That last reaction we looked at was acid-base. You have lots of questions that I can ask about acid-base. Here, the field narrows entirely. Okay? Pretty much what I can ask is based off, and I would actually never use that arrow, but what I could ask is, what kind of chemical reaction is this? Okay? And this is where it can get challenging to go through and break down. Okay? With the structure of the product shown, it becomes a little bit easier. Okay, so should we backtrack and draw the product in?
Yes.
What changed?
Formation of the
You
pi
lost.
bond.
Yeah.
Right.
You lost a pi bond.
We lost a pi bond, not the formation. That's what you meant? Okay, good. Then yes, you're right. Okay, we started with 2 pi bonds. We end with 1. That should be a giant screaming red flag that you're looking at. Addition. Okay, so you've now named the reaction type. Okay, this is an addition. This is also a mechanistic step. So we should now be able to go through and say, what mechanism is this addition?
Like as in the SN2, SN1 stuff.
Okay, so SN2,
The
SN1's a slightly different system, so we gotta throw SN1 to the side. But when we talk about what are the mechanisms, you have SN2, acid base, E2, heterolysis. I just moved that finger. God damn it. Acid base, SN2, E2, heterolysis, coordination, nucleophile elimination, nucleophile addition, electrophile elimination, electrophile addition. You have 8 different mechanistic steps, 9 different mechanistic steps.
I thought there was only 4.
Okay, so there are 9 possible mechanistic steps. Okay, could this be in SN2?
No,
Why?
because SN2 applies to substitution,
Okay, and this is applying to
addition.
addition. So we already know it's an addition. What are the possible additions? Awesome, nucleophile and electrophile. Okay, so we've got 2 choices. We have to differentiate between the nucleophile addition and the electrophile addition. What do I know about nucleophiles and electrophiles?
Nucleophiles donate electrons to form a bond.
What do electrophiles do?
They accept electrons to form a bond.
Okay. Does that help you decide which one is the nucleophile or the electrophile? If the answer is yes, that's fine. Keep your mouth shut. If it's no, let me know. Sorry, that sounded rude. I've already been yelled at for being rude today.
Is the top one that we're starting with your nucleophile? Because it's donating.
I'm not going to answer that. If you think the answer is yes, then you can hold your tongue for a second. If you think the answer is no, that information does not help you, then you can say no. So I'm going to abstain from confirming or denying your response. Sorry.
It's okay.
No, because it's based off of charge.
So it's just yes or no is helpful. So
Oh.
saying because makes, I don't know what question you're answering. So yeah, at this point, if you know that a nucleophile donates electrons and an electrophile accepts electrons, does that help you decide what kind of nuclear reaction this is? Okay, so all I need is a no. So what charge would you expect your nucleophile to be if it donates electrons? Okay, positive. If it is positive, does it have any electrons to donate?
Nope.
So what charge should the nucleophile be?
Negative.
What charge should the electrophile be?
Positive or partial positive?
Positive or partial positive. So with that information, we can now try and go back to our structures and be like, do I see negative or positive in either of these scenarios? So let's take a look at the top structure.
Can you circle them?
Gives the answer away.
Well, I know, but it's like, is that?
I get it,
that
'cause, yeah,
option's
I would
negative,
circle it,
right?
yeah.
But that one's not.
And then this one is neutral.
Okay.
So what does that suggest?
Negative, neutral.
Nucleophile or electrophile addition?
Nucleophile.
I have a negative. That's a nucleophile addition.
So yes. Okay.
Yeah, yes. Okay. It can get a little bit more convoluted than that. Okay. When we talk about running the reaction, one of the things that we want to be kind of careful of is that the addition is about breaking the pi bond. So which molecule had the pi bond break? Top molecule or the bottom molecule?
The top, because the bottom one shows that it's donating, because it has the double, or the pi bond too, and it shows that it's donating it to its oxygen. I
Which
think.
means, does it have any pi bonds in the bottom one?
It does though, because it's getting
After you do the arrow, what happens to that pi bond?
which arrow?
Because you're talking about the bottom one. You're talking about this arrow in
Yes.
purple. After it does that arrow, does it have the pi bond anymore?
Just that arrow? No.
Does this arrow show the formation of a pi bond?
I want to say yes, but I feel like it's fine.
What else do you guys have? Rest of the class. That red arrow. Does that look like the formation of a pi bond?
Well, it looks like it's pointing to the carbon.
Yeah, it's pointing to a carbon. Is it pointing to a bond? Because to make a pi bond, you have to put more electrons into a space where there is already a sigma, which means you're going from an atom to a bond to make the pi bond. Here, you're taking that arrow and aiming it at an atom. That's not a pi bond formation. That's a sigma bond formation. That red arrow is absolutely 100% sigma. What does that mean? If we look at the bottom structure, what is happening to it? It's making a sigma and breaking a pi bond. That's the one where the addition happened, because it is losing the pi bond. What happens in the top structure?
Connecting them.
Yep. Man, I keep taking pictures of my screen for the record in case anybody was panicking. Okay. What happens in the top structure? Well, we're taking the electrons in the pi bond and we're moving them to make a sigma. And if I do that, what happened to the pi bond? If I take electrons that were in a pi bond and I now move them to make a sigma, what happened to my pi bond? That's a loss of a pi bond, which would say, shouldn't the top one be the addition? Well, they both can't be the addition. Well, what else is happening in there? Look at the other arrow. What is it doing?
It's forming.
Forming a pi bond. So if we look at that top molecule, we are both forming a pi bond and breaking a pi bond at the exact same instant, which means net, what happened? Nothing. Okay? So the addition is happening in the bottom molecule. Because I know the addition is happening in the bottom molecule, this is my addition. I can now go back up to the top molecule and say, what charge was it? It was negatively charged, or my source of electrons, that had to have been the nucleophile. Kind of, sort of? So you're really zeroing in on it. I would argue, and I know there's a bunch of stuff up there, that I would never show a mechanism like that. It's technically correct for anybody that wants to challenge me online. I would show it from over here. Gotta get rid of some of those arrows. And while it's technically incorrect, I think it better shows the flow. Okay, because when we talked about our resonance structures, we had our useful versus our best. The best was the one I just erased. That's the ghost in here. Okay. I want to show it from that useful because that helps to kind of streamline the chemistry. You're now looking at it. I'm not doing this. I'm making and breaking a pi bond at the same time. It's focusing on just what the chemistry is of that molecule. Okay. So it helps to streamline and simplify the conversation in my point of view, particularly for a class like this. Does that make sense? Questions?
Are we gonna see a majority of problems on the test that look like this, or?
And so that's a fair question, and kind of my counterpoint to that would be we've spent 5 weeks talking about this unit's content. Did we spend 5 weeks looking at this content? No. We spent maybe a week. Right? So, assuming I'm not a complete jerk, which is questionable, okay, if we spent a week out of 5, you're looking at 20% of the test on this content. The rest would be back off for everything else. Okay? In some fairness, what we just talked about today covered some of that older content too, okay, because that's looking at the acid-base stuff. But we still have melting points, we still have boiling points, we have dipole moments, we have identifying ionic versus polar covalent versus covalent. Okay, all of that stuff is still there. I think you were here for that lecture, weren't you, where I summarized all the topics?
Yeah, that's gonna be on the exam.
Which is posted. In fact, I have pulled up that lecture video to get that handwritten notes of what did I say was going to be on the test so that I could help frame the exam. And I have a pretty solid draft of the test, but it is not done, unfortunately, because my wife was out of town this weekend and it's very hard to write an exam